Hi everyone, my name is Nurulhaziqah Syahirah Binti Yunus and my matric number is 150197.
Hi, my name is Fikriyah Binti Mulyadi and my matric number is 150179.
Assalamualaikum and hi, my name is Aina Nazifa Binti Sohidan. My matric number is 153171.
Hi everyone, my name is Nurulhaziqah Syahirah Binti Yunus. Today our group will be present one of the basic quality control in diagnostic radiology, which is tube potential KVP. So, what is tube potential KVP? Tube potential may be defined as the electrical potential difference between anode and cathode of the X-ray tube. Tube potential is measured in voltage or kilovoltage range in CT and commonly represented as peak kilovoltage or KVP. The peak kilovoltage KVP is known as the maximum voltage value at any time during exposure. It is an important parameter of an X-ray machine, which is a direct product of its generator circuit design and other components. Other important parameters of an X-ray machine are tube current, milliamperage MA, and exposure timer, seconds over milliseconds. The KVP test provides a measurement of the peak electrical potential across the X-ray tube when it is operating. In diagnostic radiology, the KVP is one of the most important parameters affecting both radiation exposure and image contrast. The X-ray KVP is most critical because of a small error of this variable will have a greater effect on the final radiographic image than an equivalent variation in any of the other parameters, such as tube current MA, exposure time, and focus to image distance FID. However, it is important to note that selected exposure factors such as KVP and milliampere seconds (MAS) can only be accurate if the X-ray machine is functioning optimally. Tube potential does not have a linear effect on those. The X-ray intensity reaching the image receptor after the beam passes through the patient varies approximately as the fifth power of KVP. The KVP affects not only the intensity reaching the image receptor, but also the subject contrast of the image. This is the illustration of tube potential.
The next part is test equipment. Test equipment is the user can create many of test tools. Test pattern, mesh pattern, lightweight fixtures, and timing tools are examples of such objects. Other test equipment, such as a test cassette, require calibration and adjustment, which can only be done in large quantities. Other test tools are commercially available and can be obtained from the manufacturer and his dealers. The tests were created to make use of the same simple test tool over and over again. Test equipment required for quality control of tube potential. The test uses a modified form of the KVP test cassette. Firstly, the test cassette reduced to lower energy content of the beam by means of a copper filter. After that, the beam goes through two columns of holes in a lead mask to an intensifying screen where the light from the screen exposed to the film. In front of the one column of hole is placed a copper stack wedge. Behind the screen of the second column is placed a 3-1 optical attenuator, matching the film density of the image of pair of holes, one of each column. The third valued layer of copper attenuation determines which is used to estimate the effective KVP of the beam. The accuracy is quite high and much better than form that of the mini wedge. At the bottom of this slide, this is show the picture of KVP test tube. There are two types of KVP test cassette. First, a single of column centered at 80 kVp for routine measurement. Second is 4 or more pairs of columns centered at various kVp values ranging from low value kVp memo to higher values kVp check.
I am Fikriyah Binti Mulyadi and I will continue with phantoms. So in screen film radiography, the choice of X-ray tube potential kilovoltage peak affect the image contrast. Hence, appropriate selection of tube potential kVp during X-ray examination is crucial. So what really is a phantom? A phantom by definition is a highly specialized object utilized in medical imaging for quality control, equipment calibration and dosimetry. The material of the phantom should closely mimic the human tissue. There are two main types of phantom, which are the anthropomorphic phantom and calibration phantom. So these are the examples of anthropomorphic phantoms. Anthropomorphic phantoms are objects that simulate patients made of material with similar tissue characteristic to normal biological organisms. So these two blocks are the examples of anthropomorphic phantom. On the left is transparent, and on the right is solid phantoms. So since we are discussing about tube potential, then I will be showing you the effect of using different kilovoltage on image contrast. So from the first image, these three images are generated from a pelvic phantom. So the first one is using the 60 kilovolt and radiation intensity at 141 milliampere second. Second one at 75 kV and 36 MAS, and the last one was at 120 kV and 6 MAS. So, although increasing kV will always reduce the patient dose, this also increases the amount of scatter or backscatter, hence the image has less contrast. So as you can see from the three images, when we use the highest kilovoltage, the contrast is less, especially on the third image. So these are the other examples using a knee phantom and skull phantom, using 75 kilovoltage and 125 kilovoltage. So as you can see from both pair of images, the one using the lower kilovoltage has a more prominent contrast compared to the higher kilovoltage on the right. So as the kilovoltage is reduced, the average photon energy is reduced, the proportion of photoelectric interaction increases, and the proportion of scatter event is reduced as well. So in radiology, it is generally true that high X-ray tube voltages reduce the dynamic range in radiographic image, and also vice versa. And then I will continue with the standard. Here we will discuss on the quality control of radiographic machines. So what is quality control? It is a specific test required to ensure effective and safe equipment performance. QC testings are oriented to ensure the accuracy of the diagnosis, delivery of the prescribed dose, and to minimize the dose of entrance to the patient. So QC testing has a lot more procedures, but these are the main ones. First one is the acceptance test, consistency test, status test, performance test, verification and follow-up. And this is the diagram of generally what we will do. First is the equipment purchasing, installation, and we will need to have a lot of quality consistency tests so that the equipment can be used. So these are generally the procedures of QC testing. First one is the acceptance test. It is performed on new equipment to demonstrate that it is performing within the manufacturer's specification. And then we move on to the consistency test. It is performed at specific interval to check on the performance of some key parameters. For example, tube potential. And then status test, performed with full testing at longer periods, usually annually. And then performance test, performed on an X-ray system after a predetermined period of time. And then the verification for radiation protection and QC equipment material. And lastly, follow-up. It is necessary corrective action taken in response from previous result of QC procedures. These are the examples of quality control tests that we could do. There are many more, but I just list 6 in here. First one is the peak tube potential that we will discuss later in QC methods. And then film processor monitoring, milliampere second reciprocity, focus spot size, Bucky grid centering, and radiographic illuminator.
Next, I will continue with the quality control methods of tube potential. First, the cassette is loaded with a fresh film. The cassette in the X-ray field is positioned at the recommended distance from the X-ray source. The proper technique on the X-ray control is set, which KVP to be measured, MA station at which measurement is to be made, the exposure time necessary to provide manufacturer's recommend MAS. The exposure is made, with multiple exposures, one for each KVP column. The film is processed. The film on the video box is examined to determine the copper thickness for which there is a density match. The use of a densitometer is recommended for highest precision, interpolated between steps for accuracy. Next, single tests are routine should be done at 80 kVp at one of the higher MA stations. The match step is recorded by saving the test film. The kVp from the calibration curve is determined for the voltage waveform used, either single or three-phase. Lastly, the kVp measured is recorded. By doing all the methods for the quality control of tube potential, we will get the evaluation of the result. The measurement kVp should be within plus minus 5 kVp of the set value between 65 and 95 kVp for all MA stations which are used. If the kVp is too high or too low, check that the line voltage compensator is set properly. Check the MA value with the panel meter on long exposure time, 0.5 seconds. If this have drifted, have it reset. If not, have the primary voltage reset to bring the kVp to within acceptable limits by a qualified serviceman using a high voltage divider.
Last part is conclusion. The KVP is primary controller for the penetrating X-ray and radiographic contrast. So first, the KVP as the primary controller of the penetration X-ray. The KVP controls both the quality and quantity of the X-ray beam. As the KVP is increased, the energy of the photons in the beam is increased so that the quality of the image also changes. The penetrating ability of the photons increases when the photon energy increases, resulting more photons can get through the path of body and reach the image receptor, also known as IR. Next is KVP as the primary controller of the radiographic contrast. The contrast of the image is directly affected by KVP. High KVP produces a low contrast image, while low KVP produces a high contrast image. Each body part that is radiographed will have a KVP assigned to it via the exposure technique chart. This KVP is predetermined based on the penetration needed for the part and the contrast required. So, to summarize, tube potential is an important scanning parameter for radiation dose optimization. Quality control in radiology is very important in order to ensure that diagnostic images produce a high quality, provide enough information on the cause of lowest minimum radiation exposure to the patient. So, that's all from me and my group members. Thank you.